All right, so the last rectangle that we need to deal with, rectangle number 4. As we just drew at the end of the last video, its height will be the value of our function at x equals 3/4. So again, remembering that our function is x squared plus 1. 3/4 squared is 9/16. 9/16 plus 1 is 25/16. And so its area, call that a sub 4, that'll be its width of 1/4, times its height of 25/16, which is 25/64 square units. And so there we go. We've got the area of each of the 4 rectangles we're using to approximate our region R. And so then, to get the approximation of the area A, we're just going to add these 4 areas up. So we can estimate the true area A to be. But we know this isn't going to be right. So that's why I put the little wavy equal signs in there to show that this is an approximation. But it's going to be about the area A1 plus A2 plus A3 plus A4. And if you add all 4 of those together, you'll see that they add up to be 39/32. So a little bit bigger than 1. In fact, that's about equal to 1.22. Like square units. It would depend on what the function was measuring things in. But the problem with that is that we've got no idea how good that estimate actually is. We know this is definitely an underestimate because we've definitely left a bunch of stuff out. And we can see that from our graph. We've left out this little bit, and this slightly bigger bit, and this bigger bit, and this much bigger bit, and we haven't overlapped anything, so we're not taking in any areas that we shouldn't be. So that makes this the smallest reasonable estimate for the true area A. And so we call this the lower sum. Now, the only way we're going to get any kind of a sense as to whether this is even close to the true area would be to find another estimate and compare the two. So, like we were saying at the end of the first video, a completely reasonable alternative to the way we just calculated that approximation would be to come back to our graph, but instead of always using the minimum value of the function on each subinterval to give us the height, what if we use the maximum value? Let me redraw that graph. Again, focusing on the first quadrant, because that's where all the action is, at least for this example. So draw back in the parabola. Draw back in x equals 1 and x equals 0, and the x-axis as our other boundary curves. And of course, we're going to use the exact, oh, there we go. We're going to use the exact same partition. We still think, seems very reasonable that we should want a regular partition. So we're still splitting this up at 1/4 and 1/2 and 3/4. So nothing about that element of the setup here is going to change. What is going to change will be the height. So instead, we could try using not the minimum value, but the maximum value. Of f of x on the corresponding interval to give the height of each rectangle. So in other words, we could make the rectangles as large as it seems they could reasonably be. We wouldn't be taking in unnecessary extra stuff, but we definitely are going to take in some extra stuff. When we do that, these are called circumscribed rectangles. All right. Well then, the first one, the one on the very first interval from 0 to a quarter, again, because this curve is increasing as we move from left to right, that means that the largest it will ever be on each of these subintervals will be at the right endpoint of that subinterval. So for the first one, going from 0 to a quarter then, that means we'll pick that to be the height of our rectangle. Which, yes, does mean we take in a little bit of extra region here. That's really outside R, but not a huge amount. So again, we're going to have to keep our fingers crossed that that's not too big of a deal. So then, for the first rectangle, I'm just really repeating what I did in the last video, but now with these new heights. So using circumscribed rectangles, its height will be f of a quarter, which we already computed to be 17 over 16. So its area let's call it B1 this time. Well, these are all still rectangles of width 1/4, but now a different height, 17 over 16. So that's 17 over 64. Likewise, we can do the same thing for the second rectangle. The same thing for the third rectangle. The same thing, I've done a great job of making these even, but you get the idea. For the fourth rectangle, these should all be the same width. You can pretend. But even with my slightly inept sketch here, we can see that each of these rectangles does involve slightly more and slightly more and slightly more of this extra area. So we're definitely going to have an overestimate in this case. That seems unavoidable. So I'm not going to write all of this out again in full detail, but we can say very briefly the other rectangles will have heights. Well, first of all, rectangle number 2, it has a half as its right endpoint. So its height will be f of a half, which we've already calculated to be 5/4. The third rectangle, it goes up to x equals 3/4. So its height will be f of 3/4, which again, we've already worked that one out earlier, right at the top of this video. That's 25 over 16. And then the last rectangle, through this method, its height will be the value of the function when x is 1. F of 1, well, that's just 1 squared plus 1, which is 2. So their areas then will be, well, the area of the second rectangle, B2, will be 1/4 times its height of 5/4. So that's 5 over 16. third rectangle, its area B3, will be a quarter times its height, which is 25 over 16. So that's 25 over 64. And finally, the last rectangle, its area B4 would be its width of a quarter times its height of 2, and a quarter times 2 is a half. So therefore, we can take these four areas, and just like we did in computing the lower sum, we can add those together, and that will give us a different approximation of the true area. Let's pick up there in the next video.